Okay, so this is a follow-up video for that second handout on the Taylor series. So first off, so we've talked about Taylor series, which look like this. Let's see, we've got the sum as, I'll use n. N runs from 1 to infinity. The nth derivative at a over n factorial times x minus a to the nth power. Okay. Now there's also a different type of series. Well, it's very closely related. I'm looking for the spelling here, Maclaurin. Maclaurin series. And this is just a Taylor series with a equal to 0. Okay, and so we get the same sum as n runs from 1 to infinity, the nth derivative evaluated at 0 over n factorial times x to the n power. So it simplifies things a little bit. And the issue is that it's most accurate right around 0. The further you move away from 0, the more terms you're going to need in the Maclaurin series. Okay. So let's look at a couple of really commonly used Maclaurin series, and these are for e to the x, sine of x, and cosine of x. So e to the x is actually very simple because it's its own derivative. And so all of the derivatives will be e to the x power. And so then if our a is 0, f of a is going to be e to the 0, which is 1, and that'll also be f prime of a, f double prime of a, and so on. Okay? So all the coefficients will be equal to 1 divided by the n factorial. Here it is. Okay. So our Maclaurin series for e to the x is going to start out as 1. And then we'll have plus 1 x to the first, and then 1 over 2 x squared, 1 over 3 factorial x cubed, 1 over 4 factorial x to the fourth, and frequently the variables are written in the numerator. And so let me back up and do that. We'll call this x squared over 2 factorial, x cubed over 3 factorial, and so on. Okay? So, let's see here. 1 plus x, x squared over 2, x cubed over 3 factorial, and so on. Okay? So there's our e to the x Maclaurin series. Now let's do the sine function. So f of x is sine of x, and remember a is equal to 0. So f prime is going to be the cosine. F double prime will be negative sine. F triple prime then will be negative cosine. And when we get to the fourth prime, this will bring us back to the positive sign. So this is just going to create a pattern that's going to repeat every 4 times. Okay? So, f of a, the sine of 0 is 0. Cosine of 0 is 1. Sine equals 0. Negative cosine is negative 1. This will be 0. And then, let's see here. The next one should be positive 1, and then 0, negative 1, 0, positive 1, and so on. So 0, 1, 0, negative 1, 0, 1, 0, negative 1, and so on. So there's the coefficients. So that means all of the even-powered terms from the Maclaurin series will be 0. So let's go ahead and write this out to get started with. Sine of x, we'll have 0 plus 1x, and then 0 over 2 factorial x squared, and then minus let's see here, 1 over 3 factorial x cubed, and then 0 over 4 factorial x to the 4th, and then plus 1 over 5 factorial x to the 5th, and so on. Okay, so now that we've done that, let's get rid of the zeros, okay? So there's that one, there's that one, there's that one. All right, so what we're going to get out of this sine function is only the odd powers of x with this alternating sign, okay? So this is going to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. Okay, so there's the sine function. And these are included, if you haven't looked all the way to the end of the handout, at the very end of the answer key there, you've got your Maclaurin series for e to the x, sine x, and cosine x there. All right, so let's look at the cosine function. Let's see here, let's leave some of this up. All right, so this will be cosine. The first derivative is negative sine, second derivative negative cosine, third derivative sine, fourth derivative cosine. We get the same, well, a similar repetition, okay? Let's see, cosine of 0 is 1, 0, negative 1, 0, positive 1, 0, negative 1, 0, positive 1, 0, dot, 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 okay? So a similar but sort of opposite pattern comes up when we're doing the cosine function. So let's go ahead and start writing it out the long way. So we're going to have 1, 0x minus 1 over 2 factorial x squared, 0, x cubed, let's see, and then 1 over 4 factorial x to the 4th, 0, x to the 5th, and then minus 1 over 6 factorial x to the 6th. Okay, so that's what we're getting from all of this. And then let's do the same thing. Let's go back and take out the zeros. And this time we're going to be left with even powers of x. Okay, remember this is the 0 power right here, which is also an even number. So then we'll have 1 minus x squared over 2 plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. It'll just continue doing that for all the even numbers. And actually, if you think about these even and the even and odd powers here, I sometimes remember this as even and odd functions, right? The cosine is an even function because it's symmetric about the y-axis. It's a reflection. It equals the section of the curve on the positive x-axis is a mirror image of the section of the curve on the negative x-axis. The sine function is what's called an odd function, and it has symmetry about the origin. Okay, it's got this kind of a different kind of symmetry that is typical of what's called an odd function. Okay. All right, and the sine function will have all the odd powers. The cosine function will have all the even powers. Okay, so there are those common Maclaurin series, and you can actually play around with these too. You can use these. I mean, we're not going to do this, but you can use these to show that e to the I pi is equal to, well, let's call it I theta before we get to pi. E to the I theta is cosine theta plus I sine theta. And you can show that by using these Maclaurin series. Okay? If you plug in I theta into here, you'll get the same thing as if you take the cosine series and add it to I times the sine series. It's kind of an interesting exercise if you've got some time to do it. All right, now what? Let's look at some problems. let's see here, on the second page of that handout, let's see, the first even numbered problem there is problem 10. So, we want to use the Maclaurin series for e to the x, right here. And we want to use that to approximate square root e, which is e to the 0.5 power. So, to do that, we're going to plug in 0.5 for x in all these places here. And then, let's see, we want to do this to 4 decimal places. So, we want to get this accurate to the 10,000th place. Alright, so what we're going to do is we're going to take this series, and the first thing I'm going to do here is I'm going to type in 0.5 and store that as x. Okay, that'll just make things easier for us. Then I'm going to start typing in, I'll start off with just 1 plus x is going to be 1.5, of course, and then we'll add x squared over 2, and that'll be 1.625, and then x cubed divided by 6, which is 3 factorial here, right? So 1.64583 repeating. Let's see here. And then x to the 4th divided by 4 factorial. 1.6484375. And the idea here is that we want to keep going until that 4th decimal place settles down and stops changing, right? We talked about that a little bit when we were doing Newton's method. Let's see, here's what's going on the calculator at the moment. So you can see I just started out with 1 plus x, and then I'm, just sort of progressively adding on the terms there one by one to see when that 4th decimal place is going to settle down. So let's see, I'm at x to the 4th over 4, and then we'll keep going. Plus x to the 5th divided by, at some point I'm going to go to the factorial key. Alright, so let me show you where that is here. I should have just stayed over here and done it a minute ago. Alright, well, let's take a look at it. Okay, so 4 factorial is pretty simple. 4 times 3 times 2 is 24. And once we get to 5 factorial, these numbers start to get larger. It can be really helpful to just use the factorial notation. So if you hit the math key, there's what you'll see. Across the top, you see where it says PROB right there. Arrow your way over there. Okay, and then you'll get the probability menu. And you can see choice number 4 is the factorial symbol. So let's choose that. Oops, I should have put the 5 in front of it, right? 5 factorial. There it is. And then let's see, what do we get there? 1.64869. So we're getting pretty close. You write that one down. $1.64849, 64869. And then we got to add on x to the 6th over 6 factorial. And that'll be 1.64871. And then we'll go x to the 7th over 7 factorial. And that'll be 1.64872. Okay, so These are the powers or the terms that we're working with here. And you can see the first one where that fourth decimal place settles down is right here. If we go out to the x to the 6 over 6 factorial, that'll give us an approximation of, let's see here, 1.6487. And let's see, if we use the calculator to calculate, let's do square root of e, then we get, let's see, square root e, this is going to be 1.648721, and so on. And so you can see we're getting a pretty good approximation from this. And remember, all the calculator is doing is the same thing that we're doing, it's just doing it with more terms, and it's doing it more quickly. Okay, so let's see, that was problem 10. Alrighty, let's see here. Problem 12, we want to use the sine function. Alright, let's see, I'm not going to need that anymore. Alright, so problem 12, we want to use the Maclaurin series for the sine function, and we want to approximate sine of pi over 20. Okay? And we want to do this again to the 10,000th place, 4 decimal places. So the first thing I'm going to do is I'm going to take pi over 20 and I'm going to store that as x. Alright, so pi over 20, store that as x. Alright, and then we're going to start out x and then minus x cubed over 6. So let's see here. So x is about 0.157079 and so forth. And then minus x cubed over 6 will give us 0.156433. And then plus x to the 5th over 5 factorial. And that's going to give me 1564344. So right away, that happened very quickly. 0.1564. Okay. And we can keep going. It'll just get more and more accurate. And you can check this on the calculator. Make sure you're in radians. And then you can do sine of pi over 20. And you can see it's pretty darn close. Okay. Let's see here. So that is problem 12. Now problems 14, well actually starting with problem 13, 14, and 15, we go back to the Taylor series. And so these you do kind of have to build for yourself. So let's take a look at that. So problem 14, we need a Taylor series for the cosine. So our function is cosine x. And if we're using 58 degrees, right, something that's very close to this is 60 degrees, which is pi over 3. So we can use that for a. If you've chosen to use a different a value, there's nothing especially wrong with that. It's just you're going to need a longer series. The closer your a is to what you're trying to approximate, then the fewer terms you're going to need in the series. All right, let's see here. So, derivative is negative sine. Second derivative would be negative cosine. And then, let's see, positive sine. And then we start to repeat again with the positive cosine. Okay, now this time our a is pi over 3. So remember that the cosine of 60 degrees is 1/2, and the sine of 60 degrees is square root 3 over 2. And these come from an equilateral triangle scenario, and those values for 45 degrees come from the isosceles right triangle. All right, so cosine of pi over 3 is going to be 1/2. Negative sine of pi over 3, negative root 3 over 2. Negative cosine is going to be negative 1/2. Positive sine will be positive root 3 over 2. And then we're going to start repeating, 1/2. So these four values will just continue to repeat. All right? All right. So now we need to start building our Taylor series. So I'll call it P of x because we don't know how many terms we're going to need. We're going to have 1/2 minus root 3 over 2 times x minus pi over 3 minus 1/2 times 1/2 or over 2 factorial x minus pi over 3 squared, and then plus root 3 over 2 times 1 over 3 factorial x minus pi over 3 cubed, and so on. We'll see. If we need more terms, we can add them on, but hopefully we won't need too many terms. All right, for this one, the first thing I'm going to do is I'm going to take our x value, which is 58 degrees, and I'm going to multiply it by pi over 180, and then I'm going to subtract pi over 3, and I'm going to store that as x. And then we can just evaluate 1/2 minus root 3 over 2. Well, maybe I'll store this as a different value, not x. We'll call it a. Times a minus 1/4 a squared plus root 3 over 12 a cubed, and so on. And we'll see how many terms we need. Let's see. We want 4 decimal places again. So we want 10,000th place. Let's see what we get out of this. All right, so first we got to take 58 times pi over 180, and then we're going to subtract pi over 3, and then we'll store that as a. All right, and then we'll do 0.5 minus square root 3 over square root 3 over 2 times a. Let's see here. And let's see what we get. So that first scenario right here, those first two terms give us 0.53023, approximately. 53023. Minus a squared over 4. 52992. And then we want to add square root 3 over 12 times a to the third. And that's also 52919 here. So it looks like our value for the cosine is going to be 0.5299 to 4 decimal places. All right, so here's what was going on the calculator, just so we can take a look at it. There's the value getting stored as a, and then the 0.5 minus root 3 over 2 times a, and then I continue to add on the terms until that 4th decimal place settles down. Okay, so that's it for this handout. We're going to have one more video on using this to do integrals, and so we will see you then.